So let's take a look at part B, and tell me, I can cover up the explanation and see if you have an idea about that.
Does the mechanism in A suggest that the secondary wavelets have the same frequency or wavelength as the incident wavefront? Oh, so they have the same frequency because it's the whatever oscillation started the EM wave to begin with. The EM wave has that frequency, and then that's the frequency that the electric field changes, so it's the frequency that the dipoles will oscillate, so that's the frequency of the next electric field that it gives off.
All right, excellent. That one went a lot much more smoothly. Very good. So we kind of hit that. So how can we put that into our little flow chart here? Where do those frequencies come in this little flow chart that we have on the board? But
So
that was basically a perfect explanation. That's right.
So point on wavefront gives you the frequency.
Right. I would say basically that has an oscillating E field, and that E field has a certain frequency.
And then that's the frequency of the oscillation then.
And whatever this is oscillating at, since this oscillation is causing this oscillation, you would expect they both have the same frequency.
And then it's the same.
And then there actually would be one more point. So this oscillation of this is what we would call the incident electric field from the incident wave. So the frequency of the incident electric field, that causes an oscillation of the electric dipole in the substance at the same frequency. And then that oscillation of the dipole, that causes what he calls here a secondary wave. This is the secondary wave because it's induced from the incident wave. And because this is being generated by the oscillation of the dipole, it should have the same frequency as the oscillation of the dipole, which is the same frequency as this. So you can add the frequency explanation to our little flow chart here. Okay. And we know that this is also, as you were saying, that's not really necessary for this problem, but this is also the same as the frequency of the original oscillation where the light came from originally, say on the sun or whatever. All right, so I think your answer was perfect. What does he say in the explanation? The material is driven at the frequency of the incident wave. That's basically what we said here. These two frequencies are the same. Thus, the emitted wavelengths have the same frequency. That's what we were saying here. So notice that it's good in your explanation to distinguish between the incident wave and the secondary or the emitted wave. And then he says the wavelength and wave speed may change. That wasn't something you had to explain in the question, but that would be a good thing you'd ask in another question. We already went through how that can be. When we went through, we didn't explain why the wave speed can change, but we know that if the wave speed changes, then the wavelength has to change.
Is that an important thing to know?
Why they can change? No, I don't think so. I think that was actually kind of covered in the first semester almost. But yeah, I don't think in this course, in this semester, you've talked at all about why the wave slows down in different mediums. Okay, although we know basically nothing can go faster than the speed of light in a vacuum. So we know it certainly couldn't go, the light certainly couldn't be going faster in this medium over here. Okay, so that first part we'd already explained earlier. Okay, there we go. So that's that conceptual idea. So this is definitely something you want to go back and think about again pretty soon, because it's easy for these ideas to kind of slip out of your grasp. There's a lot of stuff there. And again, we tried to go over not just this individual question, but a lot of different variations he could put on here. So we tried to explain a bunch of different things you can explain with Huygens' principle, basically. Okay. But I would certainly say this is challenging material. You can see there's still stuff here that I don't really understand all that well myself. So it's definitely, obviously, if I'm having trouble with it, it must be challenging material. Okay.